Hello everybody and welcome to my sixth tutorial about Freecad CfdOF. In this tutorial I will show you how to simulate the flow of the air around a car. So we will talk about the aerodynamics of cars and see how we can calculate the air resistance and how we can simulate the drag forces and how we can simulate the lifting forces. So let's start with Freecad. We will build up the model. First, we insert a new file and we go to the part design workbench. We insert a new body and we make a sketch. This sketch is in the XY plane. We click on OK and we can start with a design. So one of the points is that we will not meet the dimensions in the sketcher, so we have to resize it, and for that reason we start with a long line. The distance is 125 millimeter. And the length is 4.5 meters. So this means we have to change the grid to 100 millimeter. Okay. We will build up the car in a different way. So we remove this line. We start with one line. We start with the next line. Next line. Okay, now the line has finished. These lines are, this line is a construction line. We will toggle. No, sorry. So this will be a construction line, and this will be the constructions line. These constructions lines are needed for the wheels, so we will build them up with an arc. So the center is here, and we use this point and this point. These points will coincide, and the wheel will touch the ground. So, and the wheel has a diameter of 700 millimeter. So we do for the next. We will also build an arc. Take the midway. Okay, these both points will coincide, and the wheel will touch the ground. So now we need the distance between the both wheels. No, sorry, I must input the radius. Diameter is also 700 millimeter. The distance is 2.40 meters. And the distance from the front is 1 meter. The last point is away from the center 2 meters. The distance between the car and the ground is 125 millimeter, and the length of the car is 4.5 meters. So now we need one line for the front. Will be the line for the front. The length will be 500. The distance from the ground will be 500 millimeter. 549 millimeters. Then we need one arc like this. The radius will be a bit larger. The radius will be 2.5 meters. The distance from the front is, we will define. The distance from the front is 1289 millimeter. And the distance from the ground is 905 millimeter. Okay. Now we can go back to the back side. We start with a polyline. We start on this point, go up, go a bit to the, no, we will continue. Now we click 3 times on M, so we make an arc. Go forward 3 times on M. And we go down. So this point, these both points will have a coincidence. We define this coincidence. So this one is parallel. the height of the car is 1295 millimeters. So this angle is 26 degrees. This radius should be a bit smaller. This radius will be can be a bit larger. Yes, this looks good. This radius we will also define. We define this as 0.7 meters. Then we have to define the height on this point. So the height will be 795 millimeters. Now we must define this point. The distance we must define this point. The distance is 1481 millimeters. So we should take away this radius because we know the height of this point. The height of this point is given as 1234 millimeters. Now the model is complete, but we will apply in this area a small fillet. So we go here, but we want to have the constraints remaining. So we click here, click on that. And now we must define the radius. The radius is given as we will use 0.2 meters. So now our car is complete and we can pad it up. We will pad it up symmetrically to 2 meters, and this will be symmetrically to the plane. So now so here we have our car. Review the car, that looks quite good. So, but we have already inserted the wheels. But of course, we must remove some parts of the wheels because in order to have something that looks quite like the tires. So we click on this plane and define a sketch. We will use one construction line. This will be our construction line. So now we can define a rectangular. So the rectangular will coincide with this line. and it'll have a length of 700 millimeters. And it'll be symmetrically to the x-axis. And we must define a length. So we are finished. We can close. And we can use this to cut and to say we want to cut everything away. Yes, and now we can see that our vehicle has also the wheels. So now we must apply some fillets. We start with this, and we want to have a fillet of 250 millimeters. The fillet is running through the car, but that's okay. We also want to have here a fillet, also 250 millimeters. And here we want to have a fillet as well. We make it a bit larger. We say 350 millimeters. Okay, we pick this line, also 350 millimeter. Okay, now our car is complete. In the next step, we will define our simulation space. For this, we go to the part workbench and we insert a cube. We go to the definition of the cube. We make a double click on it. The length will be 11 meter. The width is 3 meters. And the height is 2 meters. Now we also change the position. In x direction, it'll be -7 meters. And in z direction, it'll be 2 meters, -2 meters. So now we have finished. We can click on OK. In the next step, we will make a cut. So we mark the cube and the fillet. The fillet represents the car. And we make a cut. And now our simulation space is defined. Furthermore, we need a second cube for the refinement of the mesh. We click on the cube and we go to this cube, make a double click on it. So in this case, the length will be 5 meters. The width is 1.5 meters. And the height is 1.2 meters. We also change the position. In x coordinate it is -2.2 meters. And in the z coordinate, we will have -1.2 meter. So that's okay. We click on OK. We will now change the labels. We call this refinement. And simulation space, we will call this car underscore cut. So now our models are complete. We can switch to the CFD workbench. First, we insert a simulation container. Next, we will define the mesh. We click on car cut and go to the measure. The measure we will use is the CF mesh. The base element size is 0.2 meters. We click on close and we go to the mesh. For this mesh, we will need some refinement. We will define this refinement. We click on cut mesh one time, go to the refinement definition. The first refinement will be an internal volume. The relative element size is 0.5. The internal volume, we will select this from the list. We take the refinement. This is solid 1. And we click on done. And now we can click on OK. And everything is OK. We make the mesh refinement invisible. So we click one time on it, press the space bar, and it disappears. So we click here on the refinement and disappear also. We click one time here, press the space bar, and now we have our simulation space back again. We go again to cut mesh, and we need a second refinement. We click again on the refinement. In this case, we will use the surface. We will have a relative element size of 0.5. We go via the boundary layers. We will have 5 boundary layers. We will define this over the surface of the car. Of course, we can click always on each surface, but this is a bit complicated. It's easier to say select from list. We select the car cut. And now the first 6 faces, they belong to the outer side. You see that you can click on it and you see where they are. So face number 6, for example, is this face. So it's easy. We can say select all. And now we deselect the first 6 faces, which are the outside faces. We click on done. And now we can close. Now our mesh is completely defined. We make a double click on cut mesh, say write mesh case. And now we can start the measure, click on run measure. This lasts about 1 minute 30. So see you later. Meshing is complete. We can review the surface mesh. We click on load surface mesh. The mesh looks fine. So we see that we have on the surface a very fine mesh. Around we have also a fine mesh, and on the cube we have a very rough mesh. I've tested this in advance, and I've also tested finer meshes, but the advantage is not very good. We will have not full convergence, but we will have acceptable results. We will see that afterwards. So we close this. We make the mesh invisible. So we click one time on it, press the spacebar, and we also make the refinements invisible. So next things, we have to define the boundary conditions. The first thing that we will need is the inlet. We click one time on the front face, go to the definition of the boundary conditions. Say this is an inlet. The velocity will be 100 kilometer per hour. Expressed in meter per second, it is minus 33.3 meter per second. You have to pay attention to the coordinate system. The wind is blowing in the opposite direction. So that's the reason why we have a negative value. We click on OK. So our first boundary condition is defined. Second will be the top face. This will be the outlet. And we will also click on the other side. We click on Add. So we have two faces which define the outlet. The subtype is static pressure. That's okay. We click on OK. Now we click on the front face. This case will be a symmetrical boundary condition. Boundary is constrained, subtype symmetric. So that's okay. We click on OK. It's defined. We now have to rotate the model round. Click on the backside. Go to the boundary conditions. And this is wall, but with no, yes, subtype is slip. So that's okay. We click on OK. Now we go to the lower side, click on this face, and also define a condition. So in this case, we have two possibilities. We can say it is like a street, so the car is moving forward, or we can say we have the condition of a wind tunnel. So this would be the conditions of the wind tunnel, but we say the car is on the street. So we say we have a translation. The speed of the translation will be minus 33.3 meter per second. So, okay. We will rename these boundary conditions. We will rename this to street. And we will rename this boundary condition to outside. So now we have to define the boundary condition for the car itself. So we go on the boundary conditions. Wall, no slip is okay. And now we can click all surfaces, but this would last very long. In this case, it's easier to say select from list. We want to have the car cut. And we will select all. But of course, the first 6 faces, these are the outside of the cube. So we deselect them. We click on Done and say OK. And now it's finished. So we can go to the other properties. We go to the physics model. We want to have steady simulation, single phase, incompressible. We want to consider viscosity. We go to the Rans model and click OK. The fluid properties are OK. We want to have air. That's OK. Click on OK. The initializing will be velocity is a potential flow. And for pressure, this is also possible to define a potential flow. So if we click on the potential flow, we click on OK. Now we click one time on the CFD solver. As I said in advance, we will not achieve the full convergence, but after 287 iteration steps, we will have a good result. So we enter 287. We make a double click on the CFD solver, write the case, We want to know the forces on the car as well. So we must edit the case. We click on Edit, go to the directory System, and edit the control dict file. Now we must enter some commands. These commands, you can find them in the tutorial by Mr. Oxtoby. I just make copy and paste, entered them. So the patches wall is a patch for the car. Density 1.2. This is the density um, of air. That's okay. And the center of rotation, yes, this will be 0 is okay. In y direction, it will be 0.6. So I assume that this is the center of rotation of a car. I did not calculate this in advance, but I assumed it's okay. And 0, that's okay as well. So we save the file, close it, go back to Freecad and start the simulation. The simulation has finished now. The simulation finished after 287 iterations. It was a number of iterations we have inputted in advance. The residuum for the pressure looks satisfying, but not very good. I've tried this also with other measures, but it will not improve the residuals for the pressure, so I chose this mesh. I have to say one thing, I had some trouble with the solver, so I just did a remesh of the model. So I just went to mesh and said write the mesh case and run the measure again. There was some issue with it. I don't understand, but if you repeat this simulation, it's good to run the measure 2 times. And now we can review the results. We can start Paraview. Now we go to the last time step. Take a look on the pressure. What we see is that we have, so here is a pressure. We have the highest pressure on the front of the car. On the top, we have some negative pressure. We will see later on that this might be a lifting force. So this car looks like an um, like the wing of a plane, and of course, a wing of a plane generates lifting forces, and so yes, we have lifting forces. So we can now take a look on the velocity. We will take a look on the velocity in x direction. So on the left, we see that we had a velocity nearly to minus 33 meter per second, and this was the boundary condition. On the rooftop, we have a higher velocity, so in some way we have some kind of compression. Behind the car, we see that we have a positive velocity. So yes, this is so the air is streaming over the car, and in the back we have uh, some kind of vacuum or something, so some kind of backflow, and this is what we see now. So our next analysis will be the steam tracer, and I hope that we can see some things. The starting point will be -7 for both points in the y coordinate. The y, we can let them like it is. and for the Z coordinate we will apply minus 0.1 and minus 0.1, and we click on no. We will reduce the resolution to 100 and we click on apply. So we see the flow over the car. We see that, as I said, we have some kind of compression and we have a regular flow, so the flow looks good. And on the back side we have something that looks quite like a turbulence. We have some kind of rotation. That looks very good. We remove the steam tracer. Next analysis will be the glyphs. We will reduce the number to 1000. We press apply. So here we have the glyphs, but yeah, for you we will use the vectors out of the elements. And to see more, we can reduce the opacity of the solid model. So here we go to the opacity, say 0.2. So we see more glyphs. We see also that we have some flow under the car, that we have a flow going over the car. We can turn it around, see on the back side. On the back side, we see that we have a regular flow into the negative x direction. This looks very good. So we have a useful result. We can also see the pressure distribution looks very good. And now we can close Paraview. We will now take a look on the forces. So we go to Edit and go to the directory post-processing. Look on the forces all. We look on the directory 0 and we take a look on the forces. So the most interesting thing for us is the force in x direction. So this means that we have a force of 390.61 Newton. But we see that we have also a large lifting force of 606 Newton. So we can calculate this afterwards into a CW value, and this would result in a CW value of 0.5. The forces we get out of the simulations can be transformed into a CW value. At a speed of 100 km per hour, we get a CW value of 0.5. At 80 km per hour, we get a CW value of 0.494. And at 40 km per hour, we get a CW value of 0.48. So you see that the CW value remains nearly constant. For the forces, I had to let the simulation run 3 times, so with 3 different speeds. The version that's implemented in Freecad currently does not allow a simulation of a ramp. The there are versions of OpenFoam which allows this, but this value is, according to my information, it's not implemented. So you have to calculate this 3 times to get 3 times the value. So thank you very much for your attention. I hope to see you in the next tutorial. Bye bye.